6.9, and we're going to be doing integrate using substitution. Now, this is something that, again, takes a great deal of practice. There's no way to avoid doing the actual practice when it comes to these types of problems. Now, what generally is happening is that we're given an integral, and or we're asked to find an antiderivative or even an integral of some function, and basically, if we can tell that it's of this form here, right? So if I'm given an integral of this form here, and determining that it's of this form is very tricky, and if we can make it look something in this form, then we can do this. We can do this in the following way. So I want to find a function whose derivative is this: f with g of x plugged in times the derivative of g. And what you do is you make what's called a substitution. So I call u g of x. So I make u equal g of x. And then I differentiate u. So I get g prime of x dx. Now, how is it that this is this? If you differentiate u with respect to dx, right? So dx u, right? Then you're going to get g prime of x. And you're going to get du dx. So that means that what you really have is, if you multiply by dx on both sides, you get sort of du is equal to g prime of x dx. And what you have here now is you have these relations after you convince yourself that I could sort of differentiate u with just putting it du is equal to g prime of x dx, right? And, well, now let's see what we have. So now I could rewrite this antiderivative as f of just u, because instead of writing g of x, I'm going to write u times, or not even times anymore, because what is g prime of x dx? Well, g prime of x dx is just du. And now you sort of simplified your antiderivative. You've made it so it's just now find the antiderivative of f of u du. And that is going to be much easier. So examples of this immediately clarify. So let's write down the general again. Let's see how this form fits in for the specific integrals that we're going to do. So f of some function plugged in, g of x is on the inside, times the derivative of g of x dx. Now let's do the actual example. Let's say I have, and I'm literally coming up with this right now on the spot, so I'm going to say, let's say I have 2x sine times sine x squared dx. And this is a good first example of how we see how we're going to match this up. So the first thing is that I actually want to take f, right? So I want f to be this sine, right? And then x squared is actually this part, right? And now you want to see that this actually is of the right form, because if I take g of x to being x squared, well, what's the derivative of g of x? What's the derivative of x squared? It's just 2x, right? So it's just switched around a little bit, right? It's just, this is the same thing as sine x squared times 2x, right? This is the same thing. I just rewrote this, and then you should see that the g of x is, right, this inside function, f is sine, and then g prime, the derivative of that inner function, is indeed 2x. So this here is indeed of this form. Now, if you look at this antiderivative, and let's take a closer look, let's just write it as 2x as I originally wrote it, because you will need to be able to identify it like this. It's probably more common to write this antiderivative like this function on the inside like this. If you look at this, right, and you sort of think to yourself, okay, well, you want to make u the thing that when you differentiate, it cancels, or it is this other part here. So in this case, right, u is just x squared. And then du is 2x dx. And now right from here, you substitute it. So now I'm going to substitute everything in. So I got the 2x that just stayed for the time being, let's say, times sine of u. And then you should sort of see that if I move the 2x over, 2x dx is just du, but I'll show you that again. So now I still have the dx here. I haven't substituted. I've only substituted for u. I only substituted x squared for u. But now I kind of want to substitute 2x dx. But we should see that I could just rewrite it as sine u and then 2x dx, right? And now I should see that this 2x dx is just du. So this here, I could just write it as du. Now there's a few other ways now. So instead of writing this, I just write what it's equal to, which is just du. And now I find the antiderivative of sine u with respect to just u. The antiderivative, right? The derivative of what is sine? Well, the derivative of negative cosine is sine plus some constant c, and then you just substitute back for what u is after you anti-differentiate. After you anti-differentiate, don't try to substitute back for u until you've taken the antiderivative with respect to u. And you want to make sure. Let's check. So I'm saying that the antiderivative of 2x sine x squared dx, or the antiderivative of 2x times sine x squared, is negative cosine x squared plus c. Well, what's the derivative of this? So what's the derivative? The derivative of cosine is negative sine, right? And this is sort of now chain rule, and substitution is the reverse of chain rule, right? So okay, so what's the derivative? What's the derivative of negative cosine x squared? Well, what that's going to be is the derivative, it's negative 1, times the derivative of cosine is negative sine. So it's going to be positive sine x squared, but then times the derivative of x squared is 2x. That's by chain rule. And then the derivative of the constant is 0, and I got back the original one. Okay. Now, there's a few ways to do this. You could have done it a little bit different when I was doing the substitution here, right? I had this dx. I always liked, when I first started doing this, I got that du was 2x dx. I liked to solve for dx directly. I like to go this, and then I'd have that dx is just du over 2. So I would directly solve for what dx is as du over 2x. So that way when I plugged in for dx, right, I wrote it du over 2x. I could see that this 2x is on the bottom and this one's on the top, and they would cancel out. And I would then wind up with this again. Because again, the 2x's would cancel, and then I'd get this, and then I would find the antiderivative of sine u, which is negative cosine u plus c, and then I substitute back, I get this, and you should see using chain rule that the derivative of this is indeed the original one. Okay, and you can do this in a whole variety of ways. Let's go over another example. Okay, so let's get another example going here. Let's see if I can do this quickly. Good. Okay, so I can do this fairly quickly. Okay, so let's get another example. So another example might be maybe something more or less straightforward. I don't know. You decide. Let's say, I don't know, a good one would be 3x squared. X cubed plus 10. And then even, will it work if I do this? Yeah, x cubed to the 11th dx. Okay? So again, right, you want to see that the derivative of this inside part is already right here. And that tells you sort of that it's of the form f of g of x times g prime of x dx. It's of this form, right, where you make this the u value. So in this case, the u takes the place of this. It's x cubed plus 10. So I write that out. U is equal to x cubed plus 10. I take the derivative of u, which is 3x squared dx. And again, I always liked to just solve for what dx was and substitute everything in, because then it was more clear to me, at least, seeing how it is that I could just kind of find the 3x squared dx here. This is 3x squared dx, so instead of both of these things, you just write du. Maybe that's quicker for you, maybe that makes more sense, that's fine. It's up to you. I'm going to sit here and I'm just going to rewrite the 3x squared to start. I'm going to substitute for what I made u, write it as u to the 11th. And then I'm going to substitute for what dx is. Dx is du over 3x squared. And then this 3 cancels this, the x squareds cancel, and I'm left with the antiderivative of u to the 11th du. And this just follows from regular power rule anti-differentiation, right? U to the 11th, you add 1 to the exponent and you divide by that same value over 12 plus c. And after you've taken the antiderivative, you plug back in for u. U is x cubed plus 10 to the 12th over 12 plus c. And you can, of course, check your work. You can take the derivative of your antiderivative to see if you get this back. So let's see if we get this back. What is the derivative of this whole thing? Well, the inside function is this right here. And you neglect that part. You just think of it like u, right? That's literally, we use the same letter. It's not a coincidence, but maybe you should use a different letter not to confuse yourself, but you can. You just say u is that inner part, and you say, what's the derivative of this here? Well, it's bring down the 12, 12 over 12 now. The u is here, the exponent decreases by 1, times the derivative of that u value, right? Well, u was x cubed, this is 1, u is x cubed plus 10 to the 11th, times the derivative of u is just 3x squared. And this here is exactly, right? I also have the plus c, but the derivative of the c is 0, so that's fine. And then this here is exactly the same thing as what I have inside here. For what they're looking for me to find the antiderivative. They're looking for me to find a function whose derivative is this. This here is a function whose derivative, and I found the derivative, is this.